following topics, in which first we are going to be discuss about your MIMO systems, what is the requirement of the MIMO, then the concept of their diversities, then definitions, how these antennas works, and what are the different forms of their MIMOs which we are going to be used. And after that, we are going to be discuss what the current requirement of their MIMO antenna systems and what the points you have to consider when you are going to be design any MIMO antenna systems. And after that, I will discuss about your some Dielectric Resonator antenna based MIMO systems in which I have currently worked. So here, the first thing is the basically your MIMO antenna system. So what is the motivation behind this work? The motivation is always basically going to be lacking with respect to your what is the current requirement of your human beings. So here we can say that the current requirement of the modern wireless communication system is relying on these three things. The first is the basically your high data rate, improved reliability, and high channel capacities. So high data rate is most important point because at present day, everybody is basically going to be wants the very high speed. For example, everybody is basically going to be do the video conferencing, and nowadays due to this pandemic situation of their COVID-19, all the classes and everything is basically going to be online. So there's a requirement of their very high data rates so that in the real time we are able to discuss the things. Similarly, the improved reliability means the system must be reliable. With respect to that, there is no lack of your security, all these things. So whatever the data we are transmitting from one place to another site, we have to think that the data is basically going to be secure and reliable. So the reliability is the basically another issue, and the high channel capacity. So high channel capacity, we can say that nowadays in our country, the population is basically going grow day by day. That means the number of users is going to be increased exponentially. So you have to design a system so that that system is going to be sustainable and it is able to support each and everyone in terms of their providing their requirement of their communication systems. So all these three things is the main requirement of their current modern communication system. So what is the possible solution? The possible solution of this particular requirement is the multi-input, multi-output antenna systems. By using this concept, we are able to fulfill these three requirements for their modern communication systems. But whenever we are basically going to go for some technology, definitely there are some advantages, but these advantages basically going to come at some specific cost. So what is the cost of that particular thing? The problem which is basically going to be like with this technology, it is the high mutual coupling or low isolation between the antenna elements. What does it mean between the antenna elements? As the MIMO name, this is multi-input, multi-output. It means we are going to have there more than one radiating element at the receiver side, and similarly more than one radiating element into their transmitter side. So we can say that in a one system we are going to use more than one antennas. So the separation between their antennas, and that separation is basically going to play their lots of role, and that separation is going to be responsible for their mutual coupling also. So here the coupling between your antenna elements is creating a lots of problem. So why we are going to do this mutual coupling analysis? Because in the current situation, we require the system very compact. Otherwise, the system is going to be very bulky. So what happens? Our task is that we want to system in such a manner that will fulfill the requirement of their modern communication system. Along with it is going to have their compact in nature. When we are going to do this compactness, then what will happen? The separation between the antenna element is going to be reduced. Due to this reduction in the separation between antenna elements, the mutual coupling between the antenna elements is going to be exponentially high. And due to this mutual coupling, the diversity performance or the performance of their MIMO antenna system is going to be drastically reduced. So that is a major challenge in the case of their MIMO antenna systems. How we are able to design this compact system, also by incorporating, we are maintaining their good mutual coupling level so that that antenna system can able to survive into their practical scenarios. So these are the basically major points which I am going to be discuss here: the mutual coupling reduction techniques, how we are going to be improve the MIMO performance, and what are the different techniques on the basis of that we can reduce the mutual coupling. Then we are going to see the increase in number of ports, because our requirement is the high channel capacity. That means we require we increase the system capacity. So that means we have to increase the number of ports. So that means this is another point that we have to discuss, how we are going to be increase the number of ports. Then the minimize correlation between their antenna elements within the Mimo systems. The minimize correlation between the antenna elements means here, whenever we are talking about your mutual coupling or isolation, so here we are going to have two different things. First thing is that the isolation means port to port isolation, that is going to be get the information from your S parameters. But when we are going to go to your field correlation, that point of view, we have to see the far field pattern of the antenna element. So both things we have to tackle, the port to port isolation and your isolation between your antenna elements. So both things we have to consider here. So that is the basically major challenge within the Mimo antenna technologies, and these are the major things which we have to address whenever we are going to work on to the Mimo antenna systems. So here, first we have to discuss what is the basic of the Mimo antennas, why we need the Mimo antennas, what are the initial technologies that are available, and what are the problems they are facing, so that we have to forcefully move on to the Mimo antenna system. So the initial system is the basically single input, single output, that is Cmo system. So in the Cmo system, the thing is that we are basically going to have only one antenna at your transmitter side and one antenna at your receiver side. That is the meaning of your single input means one antenna at your transmitter side, single output is the one antenna at your receiver side. That is the most basic kind of your communication system which we are studying during our curriculums. But here, the thing is that in this particular system, the multipath propagation is that in between your transmitter to receiver, we are basically going to have your different kind of your environments. If we are talking in terms of your city, then we are going to have your high altitude buildings, then trees, then canals are there, or rivers are there, or hills are there, or terrains are there. Different kind of their medium is there, and due to these things, our wave is basically going to the EM wave, which is going to be transmitting from their transmitting antenna to receiver antenna. They are facing your scattering, reflection, and refraction phenomena. Due to that, they are basically going to be follow their different path to reach at your receiver. So when these waves is going to be follow the different path, that means they are traveling a different distance. So at the receiver side, these waves is going to be reach at different time domain, and due to this different time slots at the receiver side, there is a problem of their mismatching and the interference, so that in the receiver side we are unable to get their proper signal. That is a major problem which we are facing into your Cmo system due to your multipath propagation. So when this problem is going to be happen, then we are going to be get these two major problems. Due to this multipath propagation, your channel capacity and link reliability both are basically going to be drastically reduced. Then what is how we are basically going to be do these things, how we are basically going to be solve this problem. Then the researchers is basically going to be moving on to your another concept which is known as your diversity. And this concept of your diversity is basically going to be used the major drawback into your Cmo system as a potential solution of your next generation technology. So that means that multipath propagation, which we are facing the major challenge, major problem into your initial systems, the Cmo systems, the same multipath propagation is basically going to be give your new solution in terms of your diversity for your next technology like your Mimo technologies. So when we are going to be define the diversity, that means the combining of your independent feeding signal paths. That means we are talking in terms of your multipath propagation. So here we are basically going to be promote this multipath propagation, and what we are going to be do, why we are promoting, because we are promoting that we are going to be design the receiver in such a manner so that the receiver is going to be check which signal is going to be have your best power, or that is going to be have your best signal in terms of their receiving power, so that our receiver is going to be select that signal, and then it is going to be recover our original message signal back. So here, if we are going to be say that our signal is going to be traveling into your 3 or 4 different paths, then there are always maximum probability at least one signal is going to be get your minimum attenuation, and our receiver is going to be select that signal which is going to be face the minimum attenuation that means that signal is going to be have their maximum power. So that means that signal is able to give their maximum, we are able to retrieve their maximum original signal from that signal. So that is the basically the concept of the diversity, where the multipath propagation is going to be used as a fundamental or as a advantageous point of view. So here you can see that the which problem that is a major problem into the Cmo system, the same problem is basically going to be converted here is the new path of the your giving the your new technology. So that is the basically major concept of the your Mimo system here. So what happened when we are going to be do this diversity analysis or diversity concept, then our signal degradation is basically going to be reduced and link performance is basically going to be increased. And that is the basically major advantages of this concept of diversity. Clear? So here we are going to have there are three different diversities: time diversity, frequency diversity, and space diversity. So time diversity means the transmission in which signal representing the same information are sent over the same channel at different times. It is a similar kind of their analysis that we are discussing in the time domain, TDM, and time domain multiple axis. Similar kind of the things we are going to be doing in the case of their diversity, time diversity. Similarly, of frequency diversity. In the frequency diversity means we are using two or more widely spaced frequency channel to send the same message, usually at the same time. That means here we are going to be use more than one transmitting channel to transmit our power. Here we are going to be use your more than one different time domain to transmit your same signal. Now third one is the basically space diversity, and that is the basically your major point for discussion here. We are basically going to be focus on to the space diversity. As a definition, if we are basically going to be see the space diversity, it means it is a method of transmission or reception or both in which the effect of fading are minimized by the simultaneous use of two or more physically separated antennas. Clear? It means here our requirement is that we have to more than one antenna at the transmitter side and at the receiver side. Only then we can apply the space diversity concept. It means this concept is going to be valid for our Mimo technology. So we are going to be focused onto your space diversity. Then when we are basically going to be get the information about your diversity, then the researchers is basically going to be use this concept into your Cmo technology. What they are doing, they are basically going to be make the system in which they are going to be use more than one antennas at their receiver side. When they are going to be do it, then what are the system they are basically going to be generated, that system is going to be known as your Cmo system, that is single input multiple output. So here we can say that at the transmitter side we are going to be have their only one antenna, but at the receiver side we are going to be have their more than one antenna. So single input means that means single antenna at the transmitter side, multi output means more than one antenna at your receiver side. So this concept is basically going to be used to enable a receiver system that receives signals from the number of independent sources to combat the effect of fading. So here we can say that this concept is basically going to be useful for your signal when we are going to be transmit signal from their more than one places to your one single places. For example, I can say that when we are basically going to be have your Wi-Fi system, or not Wi-Fi system, that is your walkie-talkie system, where we are going to have your one particular receiver and there are lots of transmitters are there. In that condition, this concept is going to be very, very useful. Similarly, we are going to be have your Meso system. As per the definition of the Meso system, that means more than one antenna is required at your transmitter side and only one antenna at your receiver side. So that is the basically going to be known as your Meso configuration or transmit diversity. So here what we are going to be do, we are basically going to be use the same data which is going to be transmitted redundantly from their two transmitter antennas, and then the receiver is able to receive the optimum signal. So this receive diversity and transmit diversity, that is your Cmo system or Miso system, both are basically going to be have their own advantages and disadvantages, but they are not basically going to be give their complete flexibility in terms of their designing. For example, they are not basically going to be give they are not basically going to be support your high data rates as well as your numbers of your user, that means your system capacity. So this system is not basically going to be fulfill our requirement for your current wireless systems or communication system. Then we have to move on to their system, which is known as your MIMO configurations, multi-input, multi-output configuration. So as the name is suggested, that means we required more than one antenna at your transmitter side and more than one antenna at your receiver side. And in between, we are going to be have your medium. And in this medium, we are going to be face your noise as well as fading problem. Due to that, our signal is going to be deteriorated. So our task is that we want to remove these problems so that we are able to receive our signal properly. So for that purpose, we are basically going to be using our multipath propagation concept so that we are able to receive our signal in much more efficient way as compared to your original Cmo system. So here we can say that when we are going to be use this concept, then we are going to be have the following advantages. Higher capacities, because we are going to be have the more than one antenna, so they are able to support more than one user at a time. So that means the capacity of the system is going to be increased. Then increase data rates, that means here we are going to be have their numbers of their antenna, that means numbers of their channels. So that means your data rate is basically going to be increased. Then coverage, when number of antennas is going to be increased, that means coverage is going to be increased. Then low bit rate and improved position estimation, because your signal strength is going to be improved. But when we are going to be have the following advantages, then definitely the system is going to be have some disadvantages also. So what are the disadvantages mainly? We are going to be have these two disadvantages, three we can say that, and many more. But the major is the basically these three: the computational complexity, channel modeling, and additional processing cost. Computational complexity means here, if we are going to be say that now we are going to be we are going to be at the 4 antennas at their receiver side and 4 antennas at their transmitter side. Clear? So that means the 4x4 combination. So here we can say that at antenna 1, we can say that antenna 1 is going to be received 4 different signals from the 4 transmitting antennas at a time. Similarly 2, 3, 4. So at the receiver side, you are going to be have 4 antennas and each antenna is going to be received 4 signals, minimum 4 signals. Then we can say that this receiver needs such kind of your system so that it can process 16 signal at a time. Clear? That is your minimum requirement. It means you have to design a system in such a manner which is going to be handle the 16 signals or more than 16 signals. It means your system complexity is basically going to be increased. When the system complexity is going to be increased, that means the cost is going to be increased. So that is the basically major problem with these systems, and due to that, the cost of the system is basically going to be increased. So when we have discussed about your Mimo technology, then we are going to be have these two major configuration of your Mimo, which are going to be used to improve the communication link. So the first one is the basically spatial diversity. Second one is the basically spatial multiplexing. So spatial diversity means in this section, what we are going to be do, we are transmitting your same information across your different channel. For example, here we are going to be have your 2x2 Mimo system. So what we are going to be do, we are basically going to be transmit the same data on your both antennas. So what is the advantage of that one? For example, if the signal is basically transmitting from antenna 1 is basically going to be distorted in the medium due to your noise or fading, then there is a chance we are able to get your signal from your antenna 2. It means in this situation, we are able to improve the reliability of your system. It means the system is going to be much more reliable. Now in the second case, the spatial multiplexing. In the spatial multiplexing, what we are going to be do, we are basically going to be do your multiplexing. That means each bit of data stream is multiplexed on a different spatial channel. That means here we are transmitting your parallel systems. We can say that 101 is going to be transmitted from their antenna 1 and 001 is going to be transmitted from the antenna 2. That means both antenna is going to be transmit your signal, both signal different manner. So what will happen? That means at a time we are able to transmit your whole signal, but here both antenna is going to be transmit your both signal in different times. So what will happen here? The speed, that is your data rate, is basically going to be increased drastically. Similarly, your link capacity. But there is a problem of the reliability here. So it is the depending upon to your application, which system you are basically going to be used, whether spatial diversity or spatial multiplexing. For example, if we are going to be design the system for your defense application, it means there the reliability of their system is the the most important concept. That means whatever the signal, whatever the information any defense person wants to communicate from their headquarters, that is the basically your most secure and most important. In that condition, we cannot lose that information. So that means you have to go for your spatial diversity. For example, in the second case, when we are basically going to be transmit any movie or any video, in that condition, we require very high data speed. Even if you are going to be lose some data, your quality of your video is not basically going to be so much deteriorated, so you are unable to watch it. In that condition, you have to go for your spatial multiplexing. So it is totally depending upon to your application, whether you are going for your spatial diversity or spatial multiplexing. Now, the performance matrices of your MIMO antennas. So here, whenever we are basically going to be have two different systems, then you have to specify some parameters. On the basis of that, you can compare these two systems, or these are the basically your some important matrices or important parameters. By using these concept, by using these values, you are able to check whether this system is going to be useful for your practical application or not. So we can judge the performance of your MIMO system based on to these 5 most important parameters. That is envelope correlation coefficient, diversity gain, mean effective gain, total active reflection coefficient, and channel capacity loss. So here, the first and most important one is the basically your ECC. So your ECC, we can say that is basically going to be give the information that how independent two antennas radiation patterns are. Clear? It means this ECC value is basically going to be give your information about your correlation between your field values of your two antennas. And that is basically going to be your most important point for our analysis, because that is basically going to be give your field mutual coupling analysis. If your ECC value is going to be good, then less than 0.5, then we can say that the system is basically going to be very good for their practical communication. So here we are going to be use this ECC for comparing or for judging the performance of their MIMO antennas, and the best value, which is basically going to be C, or extreme value that is going to be useful for the designing, that is the basically your 0.5. So here we can calculate this ECC based on to your two different formulas. The first formula that is based on to your S parameters, second formula which is based on to your field values, that is your radiation patterns. So your S parameter, that is basically going to be give your information about your port to port isolations, and the formula which is having the far field pattern, that is going to be give the information about your field mutual couplings. In general, whenever we are going to be go for your DRAs or antenna systems, that is the most important part is the basically field coupling. So that means the ECC value, which is going to be calculated with respect to the radiation pattern, is more important, is more useful as compared to your S parameter analysis. Similarly, your diversity gain. So your diversity gain, we can say that is the increase in signal to noise ratio due to your some diversity schemes, or we can say that how much the transmission power can be reduced when a diversity scheme is introduced. So we can say that this diversity gain is basically the information which is going to be give the information about your signal to interference ratio with respect to your different kind of your diversity schemes, and we are able to calculate the diversity scheme based on to your ECC values. So both parameters is basically going to be interrelated. If your ECC value is going to be improved, then your diversity gain is also basically going to be improved. So we are basically going to be, I'm going to focus on to these two parameters throughout my complete discussion, and remaining three parameters that is also basically going to be calculated with respect to your S parameters. Now, a different MIMO antenna system and their real applications. So if we are basically going to be see into your today's MIMO technologies, which are incorporated in your most consumer systems that we are going to be used. For example, your Wi-Fi routers, you can see the picture here. They are going to be normally use your 4x4 antennas for their to provide your MIMO applications. Similarly, if you go for their 4G LTE mobiles, they are going to be have their two different versions, 4x4 or 8x8. And now we are going to be move on to your MIMO, that is basically your massive MIMO or multi-user MIMO antennas, where we are going to be have use your at least more than 3 times of their MIMO antenna systems. So you can see that the massive MIMO is basically going to be used more than the 1000 number of the elements, and that we are basically going to be used into your coming technology, which is known as your full 5G technology. This is not your sub 6 gigahertz technology, which is also known as your 5G, but the actual 5G is basically into your millimeter wave, where we are going to be use your concept of your massive MIMOs, in which we are going to be use more than 100 elements to get your beam forming network, so that we can control your beam movement with respect to your different phase and different technologies. So that is the basically your requirement of your incoming situations where we are going to be use such kind of your systems. What is the minimum requirement of your MIMO antenna systems? So for the minimum requirement of your MIMO antenna systems, we can say that the first is the basically this MIMO antenna consists more than one port. It means this antenna must be required more than one port. That means at least 2 elements is required to design your MIMO antenna systems. Clear? Second thing is that all the ports associated with MIMO antenna should share same impedance bandwidth. This is the another most important point. So for example, here I have taken your one simplest geometry of your MIMO antenna system, where we are going to have your 2 elements and 2 port system. So here we are going to be have your antenna 1, that is known as a DR1, then antenna 2, which is then their DR2, and both are antennas separated by their distance d, and both are fitted with their orthogonal ports. So you can see that this is if you can see that this is your x direction and this is your y direction, then you can see that DR2 is basically fed by your y port and DR1 is going to feed with your x port. So both are the basically your orthogonal feeding mechanism here. This is the most general form of your MIMO antenna systems. So here our second concept is that all the ports associated with your MIMO antenna should share your same impedance bandwidth. That means when this DR1 is going to be operate, this DR1 is going to be have your same impedance bandwidth when DR2 is going to be operate. So you can say that here we have calculated your S11 and S22, that is your blue one and black one. Both are going to be give your S parameters, that is your reflection coefficient of your antenna 1 and antenna 2. So you can see that if you are going to be consider your minus 10 dB bandwidth, then both antenna is going to be share your same impedance bandwidth. If both are not going to be share the same impedance bandwidth, then there is a problem of your signal transmission. For example, I can say that your DR1 is going to be operate at 5 gigahertz band and DR2 is going to be operated at 6 gigahertz band. It means whatever the signal DR1 is going to be transmitted, DR2 is unable to receive, or DR2 is going to be received, DR1 is not going to be received. In that condition, it is not going to be your MIMO antenna system. It is going to be your multifunctional antenna system, and that is not useful for our particular application. So the thing is that you have to consider both the antenna elements. If you are going to use the 2 antenna elements or 4 antenna elements or 10 antenna elements, whatever the antenna elements you are using, each and every antenna element is going to be share same impedance bandwidth. Clear? And that is the basically your second most important parameter. Third one is that the isolation value between the ports should be more than 12 dB. So isolation means we are going to be go for your S12 or S21 analysis. So you can see that here we have put your orthogonal position so that the port to port difference is very high. So here we are going to be say that the isolation value is basically more than 20 dB. So that is basically another point that we are going to be see. Next, the envelope correlation coefficient is going to be,
Hello, sir.
yes.
Yes, actually, the Est1 plot, actually, it is simulated by a software, and it is basically port isolation. Okay.
Yes, port isolation.
Okay. Actually, it is measured by the corresponding signals received and transmitted by the port 1 and 2. So now the thing is that actually, is it the actual isolation between the two antennas?
No. Here I am telling two different things. These two graphs is giving the information about your reflection coefficient analysis, which is going to
Yeah.
be giving your information about your port to port things. Clear?
Yeah.
They are
Yeah.
basically going to be give your information at what the frequency range in which this antenna is going to be operate. Clear? When we are going to be
Yeah.
seeing S12 analysis or S21 analysis,
Yeah.
they are basically going to be give their port to port isolation. They are not going to be give their field to field correlation. They are going to give their port to
Yeah.
port isolation.
Yeah.
Clear? There are two different things. Field to field correlation that we are going to be calculated with respect to their far field values. And port to
Yeah.
port isolation, we are going to be calculated with respect to their S parameters. Because port is the basically your input thing. That is your input parameters. So your S parameter is going to be give your isolation. But field to
Yeah.
field is the basically your far field parameters. So that we are going to be calculated with respect to their far field parameters.
Yeah.
Clear? So here,
Yeah. So actually, sir, actually, my query was that. So, what is the significance of measuring the port-to-port isolation? Actually, the isolation is required mainly because between the radiators.
no.
Okay. So,
No, that is not the way. Actually, what happened if you are going to be go for your DRS system or any antenna systems, nowadays there is a concept of your hybrid antenna. In the hybrid antenna, what is going to be happen? Whatever the your radiating element is there, that is going to be radiate along with whatever the your excitation mechanism you are going to be use. That mechanism is also going to be participate into your radiation. It means these feed lines which are going to be used to feed your antenna, they are also participating into the radiation. In that condition, your port-to-port isolation and port-to-port antenna is requirement that you have to do it. That analysis is required. Otherwise, you cannot get your better result.
yeah. Okay.
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 So that's why I am going to be consider both things, port to port analysis along with your far field. So that's why our ECC's value is going to be depending on to your both parameters. The S parameters, that means based on to your port to port isolation. Second, based on to your far field results. So in the complete discussion, I am going to be consider both values. So here you can see that based on to your this port to port isolation, I have calculated the ECC. So you can see that within the frequency range, your ECC value is very low. This value is going to be low because here you can see that your isolation value is minus 20 dB. It is a much better value. So that's why your ECC value is going to be good. But if we are going to be calculate the ECC value based on to your far field region, that value is going to be greater than almost 0.4 or 0.0, 0.03 or zero point 0.4. As compared to the your S parameters, it is going to be the your always high. You never get the your value that is going to be equivalent to the your port-to-port isolation, because the field values is always going to be have some effect onto the your each other, because that is your far field region. In the far field region, you cannot separate totally, but there are methods based on to that you are able to do it. The same method I have applied here. I am going to be energize your both ports, both antennas. They are going to be operate. They are going to be oscillated with your orthogonal ports. That means whatever the field is going to be generated by your DR1 is going to be orthogonal with respect to your DR2. So that means the coupling is basically going to be minimum in this condition, and that's why this particular type of the arrangement is going to be more useful in their MIMO antenna systems. Now, if we are going to be go for the current literature, in the current literature, we are going to be have your MIMO antennas. They are going to be use your microstrip technology, slot technology, and the PFA technology. They are three are the basically your most studies different type of their antenna elements into their today's worlds, and each antenna is going to be have their own advantages and disadvantages. This is totally based on to the your application and your requirement, which antenna element you are going to be select. Now I will focus on to the your dielectric resonator antennas. Why I have choose the DRA as an element for their MIMO antenna system. So the first thing is that, why the DRA? So here if you see, the microstrip patch antenna, that is the microstrip technology, is the most popular technology due to its compactness and cost effectiveness. And that is the reason this antenna is basically your almost non-replaceable in today's world. But there are some problems, and due to that, this antenna is going to be face the very tough competition with respect to your other antennas. And the major problem is the basically your metallic losses and surface losses. And due to these two losses, the performance of your antenna in terms of their efficiency and gain is drastically degrade when we are talking in terms of their very high frequency. For example, if you are going to be go for their millimeter wave, in that condition, the patch antenna is basically going to be show very low efficiency. So that is the major reason we have to think onto there some other antennas where we are able to get your high efficiencies, and those antennas is going to be able to handle your more power and more bandwidth. So due to this problem, we are going to be focused on to your some another antenna, those antennas which are fabricated from your ceramic materials, which are known as your dielectric resonators. And these dielectric resonator is going to be work as a radiator or antenna. That's why the name is going to be comes with the picture, dielectric resonator antenna. So here we can say that what is a dielectric resonator first. So dielectric resonator is the basically a piece of your ceramic materials or dielectric materials. And that concept is basically going to be given by the Richmere in early 30s or 40s. But at that time, this fellow has done their marvelous job in terms of their mathematical sciences. But due to unavailability of their material technology at that time, he is unable to demonstrate its practical applications. So almost 40 to 50 years back, Okoya and Barras is the basically major person who have fabricated this DR, and they have shown their potential applications into their oscillators and filters. And from them, that is from the 60s, this concept is basically going to be your integral part of your microwave circuits for their generation purpose, especially as a filter application, as a oscillator applications. But in 1983, there is a team of their professors Stuart Long. They have done a marvelous job. What they have done, the actual dielectric resonator, which are useful for your, I can say that your oscillators, or I can say that your filter applications, they are having three major important things. The first thing is that they are very selective in nature. That means the quality factor is going to be very high. Second thing, their permittivity value, that is your epsilon r or dielectric constant, is going to be very high. Third thing is that they are going to be enclose this ceramic material with the metallic boundaries, with the metallic structure. So due to these three things, that piece of dielectric material is basically going to be your highly oscillating in nature. So that's why they are going to be used as a oscillator or filter applications. So what the Long has says, the professor has Stuart Long, what they have done, they have changed something. First they have removed your metallic enclosure and they use simple piece of ceramic material. And what they have done, they have reduces the dielectric constant of that materials. Because if you are going to be go for the definition by the permittivity or dielectric constant, that is going to be give the information about to permit the electric field. That means this is going to be give your information how the material is capable to hold the field. So here when we are going to be reduce the values, it means we are going to be reduce the capability to hold the charge or hold the field values there. So when they are going to be reduce this electric constant value, then what they have done, then they are just energized, they are just excite that DR with the help of their microwave signal. And then they have seen that the microwave signal is basically going to be excite this DR, and after some time that DR is basically going to be start radiating. Then they are wondering that how this is basically going to be radiated. Then they have done some mathematical analysis, and on the basis of that they are giving their concept of that concept is going to be based on to I can say that the rectangular cavity concept. So what they are going to be do, when we are going to be excite the signal or excite the DR, then that microwave signal is basically going to be go inside your DR. Inside the DR, we are going to be have your atoms. The power, the microwave power is basically going to be transmitted from their one atom to their another atom. In this manner, the signal is the microwave power is going to be transmitted from their one end to their another end. When the signal is going to be received at their another end of their dielectric resonator, at that time there is no metallic boundary. There is only open spaces there, and open space is going to be have their dielectric constant of 1. It means the wave is going to be from their denser material to their rarer material. It means the power is basically going to be start leakage. That means your microwave energy is going to be start leakage, and that leakage of the energy is going to be work as a radiators. So that's why they have given the name dielectric resonator antenna. Dielectric resonator work as a antenna. So that is the basic fundamental behind your dielectric resonator antennas. And when they have observed, then they got these 4 important features. Absence of metallic loss, because here the radiating element is only ceramic material, which is a dielectric in nature. That means there is no metallic structure. So there is no chance of their metallic losses. So this problem is basically completely resolved in the case of their DRA. And due to that, we are going to have their wider bandwidth, high gain, and improved radiation efficiency. And that's why it is basically going to be get their much more popularities into their researchers. And nowadays they are basically fully focused on the designing of their DRAs, which are going to be useful for their current requirement of their consumer electronics as well as their another type of their systems. So here, these are the following advantages and disadvantages. That means high radiation efficiency because there is no metallic losses. Then safe flexibilities, you can use rectangular, cylindrical, hemispherical, triangular, whatever the shape is there. Avoidance of the surface wave because there is no metal surface, there is no surface wave. And easy control over size and bandwidth with respect to your epsilon r and shape. So here, what is the major disadvantage? The major disadvantage is the basically your fabrication, because these DR or these antennas is fabricated from your dielectric materials, and this dielectric material is very hard in nature and brittle in nature. So their machining is the basically typical job. So that's why the fabrication is more complex and costly. Second thing is that to design on a specific resonant frequency as compared to their microstrip antennas, because there is no proper analytical solution is available. So here we are going to have their 3 different shapes of their DRS, and each shape is basically going to have their own advantage and disadvantage. Like your hemispherical DR is going to have their 0 degree of freedom, triangular 1, and rectangular is going to have their 2 degree of freedom. 2 degree of freedom means here we are going to have their either height to width ratio or length to width ratio. By changing any one parameters, you are able to control the resonant frequency and quality factor. So it is totally depending upon to your user whether he will use your DR cylindrical, spherical, or rectangular, or another shape. But in this particular lecture, I have discussed on the cylindrical one, so I have considered the cylindrical. So here in the cylindrical DR, we are going to have their following 3 fundamental modes: TE mode, TM mode, and hybrid modes. In TE, the most fundamental is the TE01 delta. In TM, TM01 delta. And HEM, we are going to get the 11 delta and 12 delta. These 2 are the fundamental modes. And
sir,
here,
actually, I am going to interrupt you. About T and TM, we can easily recognize the T and TM by seeing the electric field distribution obtained by any kind of software, as we have shown over here. But about the HEM and say, for example, HEM11 del or HEM12 del, so how we can easily recognize that if it is 12 del or 123 del HEM by seeing the electric field configuration? So if you can put some light on this.
For HEM11 delta or higher order modes, the main thing is that here I have shown you into your either top view or side view. So whenever you are basically going to see your distribution of your field, that is your mode identification, then you have to see your field distribution from each and every side of your DRA. For example, if you are going to have the cylindrical structure, then you see your top view as well as your side view. And then you are basically able to identify here. So for example, you can see this one HE11 delta and HE12 delta. And if you are going to be, here I have shown your side view, and here I have shown your top view. So top view means we are going to be see into your 1 to delta. So you can see that here we are going to be get there 2 complete circles. So that is basically going to be give the information about your 1 to delta. But if you are going to be see your side view of this one of HM11 delta, that is going to be give your exactly similar kind of pattern that is going to give your HM11 delta. But if you see the top view of the HM11 delta, you are going to be get the only one circle here. So here, whenever you are going to be identify, you have to see your side view and top view. When we are going to be see the both view, then only then you are able to analyze it. Otherwise, very difficult to you to get it.
So actually, just if you can slightly go ahead. So what will be about 1,3 del, for example?
Okay,
that 1,2 del is there.
I have 1,3 del. You check it. I will show you. No problem. I am going to be shown to the next class, next PPTs.
Yeah.
So here there are some different designs based on to your DRS for your MIMO applications. Now our main focus on to your isolation improvement. So in the literature we are going to have these 5 different techniques to get your better isolations. So here I am going to be discuss about your some orthogonal modes and your, I can say that the defected ground structures. I am going to be use these 2 different concepts to get the improvement into your DRA. So here I am going to represent these 3 different designs which are based on to these 3 different kind of your isolation techniques. The first one is the basic your back-to-back 16-port MIMO DRA with bidirectional pattern diversity. So here you can see that I have used the 8-element and 16-port system. So if you see about this particular one section, if you're going to be focused on the one section, I am going to be use this 2 DR back to back. That is the arrangement of this section. One DR placed onto your top side, another DR is going to be placed onto your bottom side. The top DR is going to be excited with the help of your conformal strip, and bottom DR is basically going to be excited with your conformal strip too, but that is a basically your coplanar type of the arrangement. So we can say that we are going to be have your 4 antennas onto your top, 4 antennas onto your bottom, and each antenna is basically going to be excited by your 2 different ports. So total we are going to be have your 16 ports. So the geometry is clear, and in between I have created the slots, so I'm able to connect the connectors for excitation of these DRAs. Clear? So that is basically our main structure of your DRAs. So here our first target is that the first thing is that we require more than 1 DR, that is more than 1 antenna elements to make the DRA, that is to make the MIMO system. Second thing is that all the ports is basically going to be share the similar impedance bandwidth. So from here you can see that all the ports is going to be share your same impedance bandwidth. Clear? Second part is correct. Then we are going to be focused on to the third part, where we are going to be say that the isolation, the port to port isolation is going to be minus 12 dBm minimum. So here you can see that we are able to get your good port to port isolation, that means better than minus 15 dB by using this proper arrangement. So our both is basically going to be satisfied. Now we have to focus how we are able to get such good amount of your isolation without any isolation techniques. So here the arrangement which I have put it down here, that arrangement is unique. So due to this arrangement, we are able to get the 3 different polarization, 3 different diversity techniques into one system without any additional isolation improvement methodology. And that is the major advantages of this structure. So here, if you see the both antennas, that means DR1. So your DR1 is basically going to be excited by your 2 conformal strips which are placed orthogonally to each other. So we can say that the DR1, when we are going to be excited by your port 1, then we are going to be get your HM11 delta mode, and that is going to be directed toward the X direction. Similarly, when we are going to be excite the same DR with your port 2, we are going to be get the HM11 delta into your Y direction. So if you see the both modes which are orthogonal to each other, so that means here without any additional arrangement, we are able to generate the orthogonal modes inside the your DRA. And due to that, we are able to achieve the polarization diversity here. Clear? And due to that, your ECC value, that is your field correlation, is basically going to be drastically improved because of your orthogonal fields. Second thing is the basically your pattern diversity. So pattern diversity means if you see your antennas, so here we are going to have your back-to-back concept. That means two antennas is placed onto your on the same substrate, one onto your top side, another on your bottom side. That means DR1 is going to be radiate into your positive Z direction, and DR2 is going to be radiate into your minus Z direction. That means both antenna is going to be radiate into their two opposite direction. That means we are able to get their pattern diversity. So here you can see that I am just arranging the antenna elements. By using this, I am able to generate the different diversities. And due to these diversities, our isolation value, that is your port-to-port isolation and field-to-field isolation, both are basically going to be drastically improved. And that is basically your major novelty in this structure. Third one is the basically space diversity. So you can see that space diversity here. If we are going to be see the top arrangement, and same here we are going to be having the bottom arrangement. So you can see that from DR1 to DR3 we are going to be have your D1 distance, and DR2 to DR7 we are going to be have your D2 distance. So both antennas basically going to be have onto their two different distance. Clear? So that means we are basically going to be have their space diversity here. So now you can see that I have created your pattern diversity, I have created the polarization diversity, I have created your space diversity. All the three diversities available here. And now I am going to be analyze all the antenna element with respect to each other, and we are going to be see what are the different diversity techniques except these three we are able to generate it. When we are going to do the analysis, then I have found that I am able to generate polarization plus pattern, polarization plus space, pattern plus space, and polarization pattern and space. All the different diversity in one system we are able to create it. For example, the case 1, that means polarization and pattern. When we are going to be consider only one antenna portion, where we are going to be have your back-to-back analysis. So back-to-back analysis means one antenna placed onto the top, another one antenna placed onto your bottom here. So here you can see that the top antenna is going to be radiated in the positive direction, bottom minus Z direction. And due to this orthogonal feeding mechanism, we are able to generate your two different field values, one in the X direction, other one in the Y direction. So that means in this particular, for these two DR, we are able to get their polarization plus pattern diversity. Clear? Similarly, we go for their polarization free space. So here you can see that for DR1 and DR3, if you are going to be discussed, or DR1 to DR5 or DR1 to DR7, we are going to be get their space diversity. And polarization means both all the antennas is basically going to be connected by their orthogonal feeds. So here we are going to be get their polarization plus space diversity. Then we are going to be go for their polarization pattern and space. If you are going to be see your complete antenna structure. So here antenna 1 and antenna 2 is going to be give your polarization means, that is your pattern diversity. And if you are going to be see onto these two feeding structure, we are going to be the pattern diversity. And if you are going to be connect with your different dimensions, different separation, we are going to get your pattern diversities. So here we are able to generate three different diversities along with their combination of their more than one diversities. And due to this creation of their different diversity pattern inside one structure, we are able to get their drastical improvement into their isolation values. And when I have checked the isolation values, then you can see that the maximum isolation which we are able to get, that is their 32 value, in the case of their when we are going to be have their combination of their all the different diversity schemes. So here in this structure, I can say that without applying any isolation improvement techniques, by just doing the different arrangement of their antenna elements, we are able to achieve that 32 dB isolation. And that is the basically unique in the literature. Without any isolation improvement techniques, this is the maximum value which we have achieved. This is the basically experimental verification. You can see there is a fabricated structure, and these are the basically fabricated results. Then I have done your Ecc values analysis. So these top two figures is giving your Ecc calculation based on the S parameters, and bottom two figures is going to be give your Ecc values based on to your far field method. So you can see that in the case of your S parameters, the maximum value we are able to get is nearly 0.002. But when we are going to be go for your far field region, the maximum is the basically your 0.25. So there is a drastic change with respect to the port isolation, with respect to your field isolation. Similarly, this is the diversity gain, that the MEC and the channel capacity loss. Now, the second structure is the basically your 4-element based 8-port MIMO antenna system. So now here, again, I am just using the your different DR orientation. And by putting this DR orientation, we are able to get the different kind of the your diversity techniques. And due to that, we are able to get the your good isolation mechanism, good isolation value. So the first thing is the basically evolution of the your proposed structure. So here we are basically going to be have the your antenna 1, which is going to be excited by the your conformal strip. In the second structure, what we have done, I have just placed the your second element, which is basically your not at the just beneath of the first antenna, that is having some separation. But both our antenna is going to be radiated into the two different direction. Clear? And then in the third case, I am just taking another element of this antenna B, and we are going to be rotated by the 90 degree, and we are going to be joining it. Then we are going to be get your antenna C here. So we can say that antenna 1 is the 2-port MIMO antenna, antenna B is your 4-port, and antenna C is the basically your 8-port antenna system. So here what we are do, we are basically going to be have two different feeding mechanism. The first one is the basically your conformal strip. Second one is the basically your slot technology. So both the things we are going to be used for exciting of the your DR. And these are the basically your optimized dimensions. So now first we have to check your first DR element, which is going to be excited by the two different ports. So the first thing is that we have to see whether they are going to be share your similar impedance bandwidth or not. So here you can see that both are going to be share their similar impedance bandwidth. That means the 5.5 gigahertz band is basically going to be fully captured here. Then both are the basically orthogonal to each other. So we can say that the field is basically going to be orthogonal to each other. That means this is into the your X direction, this one into the your Y direction. This is human delta mode. And now here, if you see, both antenna is basically going to be radiate into the your positive Z direction. So that means here, the isolation value is basically going to be something different. That is your ECC value is going to be changed if we are going to be calculated with respect to your far field value. But if you're going to be see the port to port isolation, so both are orthogonal to each other. So that's why we are going to be get your good isolation value. So the port to port isolation is different, field to field isolation is different, field to field coupling is different. Now I have used your second element. So we are going to be get your one in the top side, another one in the basically your bottom side. But antenna element is same. Both are basically exactly replica. The only thing is that the second is basically placed into their back side with some separation. Then again, we are going to be do your same analysis. We have to check whether they are going to be have your same shear bandwidth, and then we are going to be see what is the field values, and then we are going to be see the radiation pattern. So now you can see here, this antenna is going to be radiate in this direction, and that is going to be radiate into this direction. That means for your one element, we are able to get your polarization diversity, but for these two elements, we are going to be get your pattern diversity. Clear? So we are, by using this different arrangement, we are able to get your two different diversity techniques, polarization and pattern diversity. Then I am going to be using this actual antenna elements. Now you can see that DR1 is going to be excited, radiated into this direction. This one is this direction, this one is this direction, and that one is in there. That means we are able to cover the complete 360-degree plane by using this particular geometrical configuration. And each DR is going to be radiated in the different direction. That means this is a perfect concept of your pattern diversities. So in this structure, we are able to get your polarization diversity and pattern diversities, and also we are able to cover the 360-degree angle here. This is the experimental verification. We have fabricated this antenna structure and tested it, and we are able to get your result verified with respect to your simulated one. So now here you can see that the ECC value with respect to your S parameters. You can see how the good ECC value we are able to get with respect to your S parameters because the orthogonal placing. But if you see with respect to your far field pattern, if you're going to be see for the port 1 and port 2, you can see the far field values is basically going to be high when both antenna is basically going to be radiate from 5.2 band to your here. But if you see port 1 to port 3, it is going to be your very low because one antenna radiating into the positive direction, another one into your negative direction. Clear? So you can see that the ECC value is basically going to be actual calculation with respect to your far field method, and that is going to be give your actual practical values of your ECC. So that's why in the literature, everybody wants to your ECC calculation based on your far field method. Now the third one is the basically your two element system with dual band characteristics. So now here I have used your DGS concept along with your orthogonal mode generations. So here I am going to be use two different isolation techniques, improvement techniques for getting their good isolation. So this is giving the information about the DGS structure, and both are placing with respect to your orthogonal position. So here we are going to be use two different isolation techniques, orthogonal mode excitation plus the DGS concept. But the DGS is basically going to be get your different values. It is basically going to be create the problem with respect to your far field region. So whenever you are going to be use your DGS, you have to make sure that due to DGS, whatever the effect you are going to be face into your far field parameters, they are going to be useful for your particular application. So this is the basic evolution of their antenna structure. First, I have taken your simple annular ring shape into your antenna, and then I have radiated it. Then I have seen that we are able to get the only one peak here. That means these are basically work as a radiator. So here we can say that now, keep in mind, now in the second case, I just put your DR on the top of this particular arrangement. Then I can say that I will get your another peak. Now if you see this antenna is the perfect example of your hybrid concept. That means here the excitation mechanism along with your DR both are radiating into your far field region. It means this antenna is the basically your hybrid antenna. Now I have go on to your next condition where I am going to be use the modification into the annular ring structure. When we are going to be do this, we are able to see we are not able to get any other peak into the region, but that peak is basically going to be their wider in nature. And when we are going to be put a DR on it, we are going to be get one additional peak at their 5 gigahertz. So here we can say that these two peaks near to 4 and 5.5, they are basically due to your DR structure, and this peak is basically due to this annular ring structure. And this modification to the annular ring is somehow creating another mode into your DR. So we can say that this particular arrangement is going to be create some conditions due to that we are able to get your new mode into your structure. So here, this is the analysis. You can see that when we are going to have the annular ring, we are able to excite the TM11 mode, and which is going to be get the 2.38 gigahertz, and same we are going to be get the 2.2 gigahertz. So we can say that now this strip is going to be excited here, and at the 3.8 gigahertz, we are able to generate HEM11 delta mode, which is going to be the 4 gigahertz with respect to use mathematical analysis. In the C and D structures, we are able to generate TE01 delta mode along with your HEM11 delta mode. So we can say that here we are able to generate TE01 delta mode, and here we are able to generate HEM11 delta modes. And this one is the basic TE11 delta mode due to your annular strips. Then
Sir,
we have
actually,
gone to the
just I want to ask you another question that which software will be better in the view of simulation of Mimo antennas, that is HFSS or CST? What is your opinion and why?
both are good, sir. Both are good is totally depending upon to your user. If you are frequently, if you are expert or you are user friendly with HFSS, then it is HFSS is good. If you are user friendly with CST, then CST is good. CST is more flexible. It is going to be give your direct result for ECC calculation, for DG calculation, CCL calculation. All the diversity results you are able to calculate on single click. But in HFSS, you have to write down some code. Only then you are able to calculate it. Both are good.
Yeah,
It is totally depending
yeah,
upon your user.
yeah. But sir, one thing is that in your figure that you are showing the E-field vectors, that is this E-field vector is much prominent whenever we are using through HFSS. But whenever using through CST, we have not got any satisfied level of E-field vectors.
No, that is totally depending upon your settings. What settings you are using. Like my students are much more convenient on the HFSS, but I am much more convenient on the CST. I am
Yeah,
able to get a better result in CST, but my students are able to get in the HFSS. So we are verifying both software in single time. Whatever design we are producing, we are verifying with the CST as well as HFSS.
yeah, yeah, yeah.
So here we have done the slit arrangement, and due to this slit arrangement with the help of the surface current distribution, we are able to get. So you can see that here, when slit is not there, we are able to excite this one, but we are going to put the syllabus, then there is no excitement here. So that's why we can say that we are able to reduce the the isolation, port to port isolation, by incorporating the slit in this ground plane. Then I have verified with the experimental values. So you can see that here, the simulated value is 26 and 26. Both are basically going to perfectly match in the case of this particular design antenna. Then the far field values, you can see both are perfectly matched. And the diversity values. So you can see that this is the far field pattern, and that is due to your S parameters. So both are basically into the perfectly in their specified values. And that is a basic comparison with respect to the other antennas. So you can see that we are able to get their good values and small structure with respect to their other antennas. So here I can say that I have discussed your three different structures. The first two design is basically going to be improve the MIMO performance by orienting the DRA in different directions. And due to that, we are able to get their four specially separated radiation pattern. And due to that, we are able to achieve their multi-direction pattern diversity. So we can say that by using design 1 or design 2, that means by using your different DRA orientation, you are able to get the multi-directional pattern diversity along with more number of their independent channel. In the second one, we are basically going to be achieve the diversity performance with the help of their orthogonal mode excitation along with your DGS structure. But in the third design, due to DGS structure, your far field pattern is basically going to be somewhat deteriorated, and the gain is basically going to be reduced. So in general, if you are going to see in these three designs, I would recommend a DRA orientation for getting your better isolation performance. Then what should be your future scope of this MIMO antenna technologies? So if you are going to be see in the current situation, the DR is basically going to be one of the potential candidate into their millimeter wave, because there is absence of their metallic part and having their high power handling capacity. So you can design the massive MIMO antenna systems with the help of your Dielectric Resonator antenna as a radiating element. Second thing is that you can design the compact antennas, because the compactness in the DRA is the challenging task. How you are basically going to be reduce the size of the DRA for compact devices or for handheld devices. And third is the basically how we are able to reduce or improve the ECC values. So the ECC value improvement is the completely new area. We have explored 3 to 4 techniques in our recent papers, but still you can merge more than one techniques or more than 2 techniques to get the ECC, or you can go for your some new type of your structures, like you can use your PRS structure, EVG structures, metamaterial structure to get your better performance. So these are the some DRA based MIMO antenna systems publication. If anybody wants to refer, then they will go on these papers. These are the references. And now, thank you. So if you have any question, then please let me know.
At last, I will like to thank you, Professor Ravi Kumar Gangwar, for your beautiful and very much rich presentation, very rich technical presentation we have ever seen on Mimo. So now I will ask my students, if you have any questions regarding the simulations or any theoretical part of the Mimo, you can readily ask the question to Professor Gangwar.
Good evening, sir. Myself, Utsav Banerjee. I am pursuing PhD degree from Tripura University.